Venus should be the easiest planet in the solar system to rule out for life. The surface is around 467 degrees Celsius. The pressure is about 93 times higher than it is at sea level on Earth, and the planet is covered by an atmosphere that looks completely hostile to anything alive. By any normal standard, Venus should be finished, scientifically settled, and far outside the conversation about habitability. But that is not what happened. Scientists keep coming back to the same question, not because Venus looks friendly, but because it keeps giving them reasons to check again. That is the contradiction that makes this story stick. Venus is supposed to be the dead planet next door. The planet that proves similar size does not mean similar outcome. And yet the discussion around Venus never fully goes away. It keeps returning because the real question is not whether the surface can support life. Almost nobody serious is arguing that. But before we continue, please subscribe to the channel to give your support. Let's continue. The question is whether there is a thin part of the atmosphere, high above the surface, where conditions become less absurd, and where something microbial could at least be discussed without breaking physics. That is a much narrower claim, but it is also the reason this topic has stayed alive. So did scientists actually conclude that there is life on Venus? No, they did not. And that needs to be clear right away. There is no scientific consensus saying Venus is inhabited. There is no confirmed biosignature that settled the case. What happened is more important in a different way. A set of strange observations, especially the phosphine controversy, and later arguments about unusual cloud chemistry, forced researchers to reopen a planet that many people had mentally closed. That is the real turning point. Venus did not become proven alien territory. Venus became a planet where confident assumptions started to look weak. That matters because a lot of people heard the headlines and got the wrong idea. The real story was never scientists found aliens on Venus. The real story was scientists found something odd enough that they could not keep treating Venus as a solved world. That is a very different kind of shock. It means the planet moved from being a symbol of failure and climate catastrophe back into active scientific debate. And once that happened, the conversation got much more serious. It stopped being a joke about life in a furnace and turned into a technical argument about spectra, atmospheric layers, cloud particles, chemistry, and whether existing models are missing something important. That shift is easy to underestimate, unless you understand how Venus was treated for decades. For a long time, Mars was the responsible place to look for life. Mars had the ancient rivers, the ice, the dried lake beds, the clear geological evidence that liquid water once existed at the surface. Venus had the opposite reputation. Venus was the warning case, the planet that got too hot, lost control of its climate, and ended up as a crushing greenhouse world. Mars was the serious astrobiology target. Venus was the cautionary tale. Then that neat division started to break down. And once it broke down, the scientific whiplash was real. Suddenly you had papers, reanalyses, review articles, mission concepts, and conference discussions all returning to the same uncomfortable point. If the surface is impossible, maybe the atmosphere is where the real mystery is. That does not mean the atmosphere is safe. It does not mean the atmosphere is Earth-like. It means there may be a narrow region where the temperature and pressure stop being instantly disqualifying, even though the chemistry is still extremely hostile. That is enough to turn Venus from a closed case into an open investigation. So why is that unsettling in a bigger sense? Because if Venus, of all places, can still keep life in the conversation, then life may be harder to eliminate than we thought. That is the part that changes the stakes. Most people picture habitability in a simple way. They think of oceans, moderate temperatures, and conditions that broadly resemble Earth. Venus challenges that. If some part of its atmosphere can host life, even microbial life, then habitability is not just about comfortable planets. It may also be about narrow refuges, damaged worlds, and biology surviving in places that look completely lost from the outside. That idea makes Venus more than just a nearby curiosity. It turns the planet into a deeper warning. A world can become hostile almost beyond belief, and still maybe not be fully sterile. That does not make Venus less dangerous. It makes it more scientifically disturbing. Because then the line between habitable and uninhabitable is not as clean as we wanted it to be. Then a planet can cross into extreme conditions and still leave behind some environment somewhere. where chemistry or even biology continues under pressure. And to be clear, that is not a reason to lower standards or treat every anomaly as evidence for life. The skepticism around Venus is earned. It should be hard to convince scientists that life has anything to do with this planet. The surface conditions are so extreme that the burden of proof is massive. That is exactly why the recent attention matters. Researchers are not returning to Venus because the case is easy. They are returning because the case refuses to stay dead. That is a different kind of problem. It means the data are not letting the planet remain emotionally simple. And that is where the story becomes stronger, not weaker. If Venus were obviously alive, the mystery would be smaller. You would just be waiting for confirmation. But Venus is not giving that kind of answer. Instead, it keeps producing signals that are unresolved enough to demand attention and uncertain enough to resist easy conclusions. That is why this topic has lasted. The planet is sitting in a narrow zone between dismissal and proof, and that is where science gets uncomfortable. So the stakes for this story are not cheap or sensational. This is not about forcing a dramatic answer onto weak evidence. It is about following a real scientific question that has become too serious to ignore. Are there atmospheric fingerprints on Venus that standard explanations still cannot fully account for? If there are, what is producing them? Is it a measurement problem, unusual chemistry, geological activity, or in the most extreme case, life? Those are very different answers, but all of them matter because all of them mean Venus is stranger than the old picture allowed. And if the answer ever does point to life, even at the smallest microbial scale, then Venus does not just become another world with organisms on it. It becomes evidence that planetary evolution, climate collapse, habitability are more complicated than the Earth-centered version most people grew up with. It would mean a planet can become a ruin at the surface and still maybe keep a biological niche somewhere above it. That would force a rewrite of how we think about life in the solar system, and also how we think about hostile planets around other stars. That is why this story matters before anything is confirmed. Venus is dangerous to our assumptions. It keeps pressuring the idea that we already know what a dead world looks like. It keeps raising the possibility that a planet can look completely finished and still hide active chemistry that does not fit neatly into the old categories. And if that chemistry turns out to be biological, then one of the most hostile worlds near Earth would become one of the most important discoveries in planetary science. So the real reason this headline refuses to die is simple. Venus should have been ruled out, completely and permanently, and it was not. Not because scientists gave in to hype, but because the planet kept putting unresolved evidence back on the table. That is why people are still talking about it. Not because the mystery is solved, but because it is now strong enough that ignoring it looks less scientific than facing it directly. Venus is not compelling because we have certainty. Venus is compelling because the uncertainty has become too serious to dismiss, and the next question only gets worse. If the planet is this hostile, then why did anyone start looking there again in the first place? Venus sounds like the wrong planet to talk about life. And on the surface, that reaction is completely correct. If you go by the hard numbers, Venus should have been the last place anyone looked. The surface sits at around 467 degrees Celsius, which is hot enough to melt lead. The atmosphere near the ground is so dense that the pressure is about 93 times what you feel at sea level on Earth. If you stood there, which you obviously could not, the force pressing on you would be like being deep under an ocean. Except instead of cold water, you would be inside superheated gas. So when people hear the phrase life on Venus and immediately reject it, that instinct is not irrational at all. It is the normal response to one of the most extreme environments in the solar system, and that is what makes Venus so disturbing as a scientific target. This planet is close to Earth in size, close to Earth in broad planetary type, and still ended up looking like the opposite of everything people associate with habitability. Venus is often called Earth's twin in size, but that label can be misleading if you do not say the second part. It is a twin by dimensions, not by outcome. One planet kept liquid water, stable surface conditions, and a biosphere. The other became a world where the ground is hot enough to destroy almost anything we would ever send there. That gap is the reason later clues from the atmosphere feel so strange. They are not appearing on a mildly hostile planet. They are appearing on a planet that looks almost designed to shut this conversation down. So what actually made Venus become this extreme? The biggest reason is not just that it is close to the Sun. The real problem is the atmosphere. Venus is dominated by carbon dioxide, and that thick atmosphere traps heat with extraordinary efficiency. This is where the story becomes bigger than one planet, because Venus is the clearest example in the solar system of how an atmosphere can completely control the fate of a world. A lot of people assume the hottest planet must be the one closest to the Sun, but that is not true. Mercury is closer to the Sun than Venus, and yet Venus has the hotter surface. That fact matters because it breaks a very simple way of thinking. Distance matters, but it is not the whole story. Atmospheres matter so much that they can outweigh distance and reshape the entire climate of a planet. That is why Venus is not just hot, it is a full case study in runaway greenhouse physics. The atmosphere became so good at trapping heat that the planet crossed into a state of climatic overkill. Heat comes in, and the atmosphere does not let enough of it escape. Over enormous timescales, that creates a world where the surface is held under crushing, relentless heat. Venus did not just get warm and dry, it ended up in a condition where the climate system itself turned into the main enemy. That is why scientists use Venus as a warning when talking about planetary evolution. It shows how far a rocky planet can go once its atmosphere stops acting like a stabilizer and starts acting like a trap. But even that does not fully capture how hostile Venus is, because the danger is not only down at the surface. The atmosphere itself is chemically brutal. The clouds of Venus are not made of water droplets like the clouds on Earth. They are made largely of sulfuric acid droplets, and not weak acid either. Studies describing those cloud particles put the concentration at roughly 80 to 98% sulfuric acid by mass. That is an extreme environment by any standard. So even when people start talking about the more interesting part of the Venus story, the possibility of a higher atmospheric layer where temperature and pressure become less severe, the chemistry is still a huge problem. You are not moving from hell to comfort. You are moving from one kind of impossible to a narrower and more technical kind of maybe. That distinction is very important, because otherwise the cloud hypothesis gets misunderstood. The claim is not that Venus has some hidden Earth-like region floating above the surface. It does not. The claim is only that there may be a thin altitude range where some physical conditions stop being instantly absurd for life, even while the chemistry remains deeply hostile. That is a much weaker statement, but it is also the only reason the idea can be taken seriously at all. Once sulfuric acid at those concentrations is part of the picture, nobody gets to pretend Venus is secretly comfortable. Even the most optimistic version of the story still takes place inside an atmosphere that looks dangerous at every level. So why did scientists dismiss Venus as a life target for so long? Because they had very good reasons to. This was not laziness, and it was not bias in the careless sense. It was evidence-based judgment. If you focus on the surface, Venus looks far more useful as an example of planetary catastrophe than as a place to search for biology. It is extremely hot, extremely pressurized, dry, chemically aggressive, and globally covered by clouds that make direct observation harder. There was no obvious reason to put Venus at the center of astrobiology when Mars was offering dried river systems, polar ice, sedimentary history, and a much more familiar path into the question of past habitability. That is exactly why the later shift toward Venus mattered so much. Scientists were not revisiting a world that had always looked promising, they were revisiting a world they thought had already failed the test. And when that happens, the psychology of the story changes. The skepticism becomes part of the structure, not an obstacle to it. People were right to be doubtful. They still are. But then Venus kept producing atmospheric oddities, cloud chemistry questions, and unresolved signals that made total dismissal harder to defend. That is the tension. The skepticism was earned, and the data still refused to let the planet stay simple. That is also why Venus feels different from a lot of other space mysteries. Usually, the tension comes from wanting a surprising result. Here, the tension comes from a planet resisting the role scientists gave it. Venus was supposed to be settled in emotional terms. It was the scorched twin, the greenhouse disaster, the place where life had no realistic path. It had a clean narrative, and clean narratives are comfortable. But science becomes much more dangerous when a world with a clean narrative starts producing unresolved evidence. Because then the problem is not only the new data, the problem is that your old certainty may have been built on a picture that was too narrow. And that is the real reason Venus should have been the last place anyone looked. Everything about the obvious version of the planet says, stop. The surface says stop. The pressure says stop. The carbon dioxide says stop. The sulfuric acid clouds say stop. If you only saw those facts, you would close the case and move on. But the Venus story did not end there, and that is what gives it so much force. The question is no longer whether the old rejection made sense. It did. The question is why, despite all of that, the planet kept producing enough atmospheric weirdness to pull serious scientists back in. Because once that starts happening, certainty turns into vulnerability. The danger is not that someone found an alien city or some dramatic proof of life. The danger is that a planet we treated as a closed case may still be chemically active in ways we do not fully understand. And if the chemistry is still that unsettled, then the next step gets more uncomfortable. If the surface is this deadly, then what is hiding in the one layer above it that keeps forcing the argument back open? The strangest thing about Venus is that the planet is not equally impossible at every height. And that single fact is the reason this entire story exists. If you stay down at the surface, the case is closed. It is too hot, too dense, too hostile. But if you go high enough into the atmosphere, the picture changes in a very specific way. At roughly 50 to 60 kilometers above the surface, pressure and temperature move into a range that starts to sound much more familiar. Near 50 kilometers, the pressure is around what you experience at sea level on Earth, about 1 bar. And as you go upward through that band, the temperature drops from very hot into a range that becomes much more discussable. Not safe, not friendly, not Earth-like in any complete sense, but no longer instantly absurd. That is the key structural idea in the whole Venus story. The planet is not one uniform wall of extreme conditions from top to bottom. There is a narrow atmospheric band where some of the basic physical conditions stop immediately, killing the idea of life. That does not prove anything, but it changes the conversation from impossible to testable. And that is a major difference. The reason scientists keep returning to Venus is not because they found a comfortable environment. It is because they found a limited altitude range where the physical argument against life becomes less absolute. But that does not mean Venus suddenly becomes a good place for biology. That is the part that has to stay clear. Earth-like pressure is not the same thing as Earth-like habitability. Even in that more interesting altitude range, you are still inside an atmosphere dominated by carbon dioxide. You are still inside a cloud system made of sulfuric acid droplets. You are still dealing with a place that would be chemically brutal for known life. So the cloud layer idea is not that Venus has some hidden sky, with blue air conditions waiting above the surface. The real claim is much narrower. It is that there is a slim region where a few bulk physical conditions become less impossible, while the chemistry remains deeply hostile. That distinction matters because it keeps the whole discussion grounded. A lot of weak versions of this story make it sound like scientists found a secret, habitable zone floating over a dead planet. That is not what the data say. What they say is much more technical and much more interesting. They say there is an altitude band where temperature and pressure stop immediately ruling the idea out, which means the real barrier becomes chemistry, microphysics, and whether anything could tolerate or modify that environment. That is a harder question, but it is also a real scientific question instead of fantasy. And once you start looking at the cloud system itself, the picture gets more concrete. Venus does not just have a vague haze hanging over the planet, it has a structured cloud deck with real vertical boundaries. Historical measurements place the lower cloud boundary at roughly 48 to 50 kilometers above the surface. Cloud top studies and later observations put the upper cloud region around 70 to 75 kilometers. That means the atmosphere scientists are discussing is not some undefined blur. It is a layered system with altitude-dependent temperatures, distinct chemical behavior, and measurable transport between levels. That changes the tone of the whole subject. Now, you are not talking about random speculation that microbes might float somewhere in the sky. You are talking about a defined atmospheric regime that has a real vertical profile. It has lower cloud levels, middle cloud levels, upper cloud levels, and each of those layers behaves differently. The chemistry changes with altitude. The temperature changes with altitude. The amount of sunlight changes with altitude. The cloud particles themselves vary. Once you understand that, the idea becomes easier to take seriously at a technical level. Not because it looks likely, but because it is now something instruments can study directly. And then the story gets even stranger. Because this atmosphere is not sitting still. Venus has one of the most unusual atmospheric behaviors in the solar system. Its upper atmosphere moves in what scientists call superrotation. The atmosphere circles the planet in roughly 4 Earth days, while the solid planet itself takes about 243 Earth days to rotate once. That is an extreme mismatch. The sky is moving around Venus far faster than the planet underneath it. So if there is any important chemistry happening in the cloud deck, or in the boldest version of the story, any biology, it is happening inside an environment that is constantly moving, constantly mixing, constantly redistributing material around the globe. That matters because life, if it existed there, would not be sitting in one quiet place. It would be inside a dynamic atmospheric system. Droplets move, gases move, sunlight varies with altitude and circulation. Material can be lifted, mixed or transported into harsher regions. Any chemical signature in the clouds would be shaped not just by local conditions, but by a global atmospheric engine. That makes Venus harder to interpret, but it also makes the cloud deck more scientifically important. You are dealing with a connected planetary environment, not a static pocket. And this is why the cloud hypothesis survived when the surface hypothesis did not. The surface of Venus is too extreme to keep the basic question open. The cloud deck is different. It is still dangerous, still acidic, still dry by the standards of known biology, but it is organised enough and physically moderate enough in one narrow band to keep researchers interested. There is circulation, there are suspended droplets, there is sunlight, there is chemistry. And there is a globally connected fluid system that can carry material over enormous distances. That is enough to treat the atmosphere as an active environment rather than just empty weather. This is also where the emotional shape of the story changes. Venus may not have liquid oceans on its surface today, but high in the atmosphere it has something that, for science, fills a similar role in one limited sense. It is a connected fluid environment with layers, transport, and chemical interactions happening continuously. Again, that does not make it habitable in the easy sense. It makes it coherent, and coherence matters. A place where droplets, trace gases, radiation, and circulation interact in stable patterns is a place where processes can persist. Once persistent processes exist, scientists have something real to test. That is why the cloud deck idea is much harder to dismiss than it sounds at first. Not because the environment is nice, but because it is structured. It has boundaries. It has motion. It has energy input. It has chemistry that changes with height. It has a narrow band where the physical conditions are much less extreme than the surface below. That combination is enough to keep the question alive. You do not need Venus to become welcoming. You only need it to stop being uniformly impossible. And that is exactly what happens in this one layer. Of course, none of this solves the biggest biological problems. The acid is still there, the water limits are still severe, the carbon dioxide still dominates. Any life hypothesis still has to explain how anything could tolerate the droplets, avoid destruction, and maintain itself inside such a difficult atmosphere. But without this altitude window, the whole story would collapse immediately. This layer is the reason the argument exists at all. It is the crack in the case against Venus, small but real, and once scientists noticed it, they could no longer treat the planet as simple. So when people ask why Venus keeps coming back into the life conversation, this is the answer. Because above one of the worst surfaces in the solar system, there is a narrow atmospheric zone where impossible becomes physically discussable, and that is enough to force a second look. And once that second look began, one molecule in particular turned the whole planet into a major scientific controversy. One molecule was enough to reopen a planet people thought was finished, and that molecule was phosphine. The reason it hit so hard is simple. On a rocky planet with an oxidizing atmosphere, like Venus, phosphine is not supposed to be easy to make in large amounts. On Earth, phosphine is mainly linked to biology and industry, not to normal background atmospheric chemistry. So when a 2020 claim said there might be phosphine in the atmosphere of Venus at parts per billion, levels. The reaction was immediate. Not because phosphine automatically means life, because it does not, but because phosphine on Venus would mean something big is happening. Either the chemistry is much stranger than expected, or some geological process is doing something major, or in the most extreme reading, something alive is involved. None of those options are small. That is why the phosphine story landed so differently from a normal trace gas claim. If someone announces a minor atmospheric molecule on a planet that is already chemically well understood, the story usually stays technical. This did not stay technical. It went global almost instantly. The reason is that Venus was supposed to be a planet where the astrobiology case had already been shut down in practice. Then one reported signal, tied to one specific kind of molecule, suddenly forced people to take a second look at the whole planet. That is how fast the tone changed. Venus went from being mostly a warning story to being an active scientific argument again. And the original claim did not sound small. The early reports, based on observations involving the James Clerk Maxwell telescope and later analysis from ALMA, were interpreted by supporters as evidence for phosphine at roughly the tens of parts per billion level in or near the cloud region. That is the kind of number that immediately raises the stakes, because phosphine is a highly reduced gas, and Venus is not the kind of place where you expect that gas to just sit around comfortably. In an oxidizing atmosphere, a molecule like that should be chemically awkward and hard to maintain. So the logic was direct. If the signal is real, and if the amount is really that high, then something has to be making it, and making it often enough to replace what gets destroyed. That is why one molecule was able to destabilize an entire narrative. Phosphine was never just another strange gas. It was a stress test for the whole model of Venus. If phosphine is really there in meaningful amounts, then the question is not just what it is. The question is what source is replenishing it. And once you ask that, every part of planetary science gets pulled in. Now you have to think about photochemistry. Because sunlight should break molecules down, you have to think about atmospheric transport, because maybe the gas is produced in one region and moved to another. You have to think about calibration and spectral line identification, because maybe the signal is being misread. You have to think about cloud chemistry, sulfur compounds, vertical mixing, and possible geological inputs from deeper below. One reported gas forces all of those systems to answer at the same time. That is also why the phosphine debate was never really about a simple buzzword like biomarker, even though that is how a lot of the public heard it. Serious researchers were not saying phosphine equals life. The real issue was that phosphine on Venus would be hard to explain cleanly with the baseline models many scientists were using. So the molecule became important because it acted like a pressure test. Either the observation was wrong, or the identification was wrong, or the chemistry models were missing something large, or the planet was doing something genuinely unexpected. Every one of those outcomes matters, even before you talk about life at all. And this is where the story gets stronger, because the claim survived as a major scientific topic, even after pushback started coming in. It did not survive because everyone agreed. It survived because the disagreement was serious. That is a very different thing. One side challenged whether phosphine was there at all. Another side argued that if the signal was real, then the normal non-biological pathways people had considered still struggled to explain the reported amount. That is why the story refused to die. It was not living on hype alone. It was living because the conflict itself exposed a deeper problem. Venus was either being observed incorrectly in a very public way, or its chemistry was more incomplete than many people were comfortable admitting. That creates the exact kind of tension that keeps a planet in the spotlight. If the gas is not really there, then one of the most famous recent detections in planetary science became a lesson in how hard Venus is to observe. If the gas is there, but only under certain conditions or at certain heights, then Venus is even more chemically complicated than it looked at first. And if the gas is there in a way current models cannot explain, then researchers are left with a much bigger problem than one molecule. They are left with a planet whose atmospheric behaviour does not fit neatly inside the old framework. That is why phosphine mattered so much, even though it proved nothing by itself. It hit the exact weak point in the story people thought they already understood. Venus was supposed to be extreme but not ambiguous, dead but not confusing, hostile but not full of unresolved atmospheric signals that keep coming back. Phosphine changed that. It forced astronomers, chemists, and mission planners to treat Venus less like a symbol and more like an unsolved system. Once that happened, the conversation got more serious very quickly, and the correction here is important because it actually makes the suspense worse. Phosphine did not prove life on Venus. It did something more disruptive. It removed the comfort of dismissal. It forced people to admit that the atmosphere of Venus might contain one of three things: a major observational mistake, a major missing chemical pathway, or a major biological shock. None of those options are minor. A big observational error would mean one of the most talked about planetary detections in years did not survive scrutiny. A missing chemical pathway would mean the atmosphere is running chemistry we do not yet understand well enough. And a biological explanation, even if it is the least conservative option, would be one of the biggest discoveries in the history of planetary science. That is why phosphine should be seen as the spark, not the verdict. It did not settle the case. It reopened the case. It made Venus scientifically dangerous again, because now the planet was no longer easy to categorize. A world people thought was done was suddenly back in active dispute, and the more experts looked at it, the less clean the picture became. That is when a real mystery starts. Not when one side wins fast, but when the data force everybody into a fight they cannot ignore. And once that fight began, the story got even harsher, because the next stage was not celebration. It was a full technical war over whether the signal was even real in the first place. The moment phosphine was announced, the real fight started. And it was not a fight about headlines, it was a fight about the data itself. That is what makes this part of the Venus story so important. The backlash was immediate, technical, and relentless. Researchers went back into the observations and started testing every step: the signal processing, the calibration, the subtraction methods, the shape of the spectral line, and whether the feature people were calling phosphine could actually be something much more familiar. Very quickly, sulfur dioxide became one of the biggest alternative explanations. Then a 2021 reanalysis went further and argued there was no convincing evidence of phosphine in the disputed datasets at all. That is how brutal real science works. One dramatic claim appears, and then a lot of very skilled people spend years trying to break it. And that part matters, because people sometimes hear scientific disagreement and assume the original work must have been sloppy. That is not what this means. This means the claim was big enough that it had to survive the hardest possible scrutiny. Venus is not a topic where researchers can afford to be casual, especially not after a molecule like phosphine gets connected to possible biology in public discussion. Once that happened, every detail became a target. If the signal was real, it had to survive reprocessing, alternative models, alternative line identifications, and independent limits from other observations. If it could not survive that, then the claim had to shrink or collapse. There was no middle ground where the original announcement could just remain untouched. And then came one of the strongest reality checks in the whole story. A later study using SOFIA, the Airborne Infrared Observatory, placed a very tight upper limit on phosphine in the higher atmosphere of Venus. The result was about 0.8 parts per billion, as a disk averaged upper bound in the roughly 75 to 110 kilometre altitude range. That is far below the more dramatic numbers that made the original claims so explosive. And that changes the shape of the story in an important way. It does not automatically erase every version of phosphine, because the atmosphere of Venus is layered and complicated. And different observations probe different regions, but it does narrow the possibilities. It tells you that if phosphine exists, it is not simply sitting there in a broad, strong, obvious way across the upper atmosphere. That is a huge shift. The question is no longer, did they find phosphine on Venus full stop? The question becomes much harder and much more specific. If phosphine exists, where exactly is it? At what altitude? In what amount? Is it global, local, temporary, patchy, or tied to some particular atmospheric condition? And if it is there only in a narrow region, why is it so hard to pin down consistently? That is what the data war did. It took a headline and turned it into a much sharper technical problem. And this is exactly where Venus becomes an observational nightmare. It is bright, nearby, cloud-covered, chemically messy, and difficult to analyze with instruments and methods that are often pushed to their limits on targets like this. A lot of the tools used in astronomy are built around cleaner, dimmer, or more straightforward sources. Venus is not straightforward. It is a powerful source with dense cloud layers, strong atmospheric structure, and overlapping chemical signatures that can make subtle line detection very dangerous. That means researchers are often operating near the edge of what remote spectroscopy can confidently separate. Small choices in data reduction can matter. Small assumptions in the model can matter. Confusion between molecules can matter. So this was never just a case of one team being right and everyone else refusing to accept it. It was a case of scientists trying to extract a weak and highly consequential signal from one of the hardest planetary targets in the solar system. That is why the argument lasted. The data were not clean enough for easy victory, but not empty enough for easy dismissal either. That is the exact zone where scientific controversy gets deep, because both sides can point to real technical issues. Supporters could say the signal still deserved explanation. Critics could say the evidence did not survive careful reanalysis. And in the middle of that, Venus kept refusing to become simple again. That is what makes the uncertainty powerful, instead of boring. Every outcome creates a bigger problem. If the original signal was just an artifact of processing, then one of the most publicized atmospheric detections in recent planetary science fell apart under scrutiny, which is a big story by itself. If the signal was real but highly patchy, or tied to a narrow altitude range, then Venus may be chemically even stranger than people first thought. And if sulfur dioxide is the real source of the confusion, then that does not calm the story down either, because sulfur dioxide is itself part of a larger and unresolved chemical problem on Venus. So no matter which way you turn, the uncertainty keeps the pressure on. That is why this section matters so much for pacing. A lot of space stories get weaker when the first exciting claim starts getting challenged. This one gets stronger, because the challenge itself becomes the story. The more researchers argued over the phosphine data, the clearer it became that Venus was not behaving like a settled world. Either the observations were more fragile than people realized, or the atmosphere was more complicated than people realized, or both. That is not a dead end. That is exactly the kind of situation that pulls more scientists in. And there is a hard truth sitting underneath all of this. Weak claims die quickly. If a result is flimsy, the community tears through it, finds the flaw and moves on. But when a claim gets attacked from every angle and still refuses to vanish completely, that tells you something important. It tells you the problem is real, even if the first answer was not. That is what happened here. Phosphine on Venus remains disputed enough that no honest script can present it as settled evidence for life, but it also remains unresolved enough that researchers still describe the source question as open. That balance is what gives the topic so much force, because now the story is no longer about one paper. It is about a planet forcing science into an uncomfortable position. The data do not behave cleanly enough to close the case. The criticism does not land cleanly enough to raise the mystery. And that leaves Venus in a very unusual place. Not confirmed, not dismissed, not solved, not ignorable. That is why the phosphine story survived the backlash. Not because it won, but because the planet itself kept the deeper question alive. And once phosphine stopped being a simple yes or no issue, another molecule kept pushing its way back into the case and making everything harder. Because if sulfur dioxide is part of the explanation, then Venus is not getting less mysterious. It is getting more chemically active than people were ready for. The phosphine argument gets most of the attention, but there is another gas that keeps forcing its way back into the story, and in some ways it is even more important. That gas is sulfur dioxide. If you want to understand why Venus stays so difficult to explain, you have to take sulfur seriously. Venus is not just a carbon dioxide planet. It is also a sulfur planet. Sulfur dioxide is one of the main gases involved in building the sulfuric acid clouds. And under sunlight at high altitude, it should be broken apart relatively quickly. So if you keep seeing strange behavior in sulfur dioxide high above the clouds, that is not a small details. That is a sign that the atmosphere is still being fed, still being mixed, or still doing chemistry that is not fully pinned down. That is why sulfur dioxide matters so much to the life discussion, even when nobody is claiming sulfur dioxide itself is a biosignature. It can imitate other signals, it shapes the cloud chemistry, and it may point to processes that connect the upper atmosphere to the deeper planet below. So every time sulfur dioxide behaves in a way scientists did not expect, it does two things at once. It makes the life case harder because it provides a non-biological explanation people have to take seriously. And it makes the whole Venus story deeper because it shows the planet is chemically more active than the old simple version allowed. And this is not just a vague impression that the atmosphere feels complicated. There is hard observational history behind it. Venus Express saw major changes in sulfur dioxide in the upper atmosphere over time. ESA summaries described a strong early increase followed by a sharp decline, and one detailed study reported about an order of magnitude drop above the clouds between 2007 and 2012. That is a major shift. This is the kind of number that tells you the atmosphere is not chemically frozen. It is changing on timescales short enough for humans to track directly. When you see that kind of swing, you cannot keep treating the atmosphere like a static background. You have to start asking what is driving it. So what drives a change like that? Is it photochemistry, where sunlight destroys and reshapes molecules at different rates? Is it circulation, where material from lower levels is being transported upward in bursts or cycles? Or is it volcanic input from below, with fresh sulfur gases being injected upward and then later fading out? The important thing is that all of those possibilities imply an active system. None of them fit the comforting idea of Venus as a dead, chemically settled world. The atmosphere is doing something. The real fight is about what exactly that something is. That is where sulfur dioxide becomes a major part of the phosphine war. Because once researchers started reanalyzing the phosphine data, sulfur dioxide kept showing up as one of the strongest alternative explanations. Some of the spectral features and some of the modelling choices can blur the distinction. That means sulfur dioxide is not just another gas in the Venus atmosphere. It is the gas that keeps stepping into the case every time phosphine is discussed. Every time someone says maybe this line points to phosphine, the next question is, or is this sulfur dioxide instead? Or is sulfur dioxide shaping the analysis in a way that changes what that line really means? That is why sulfur dioxide is so important for the pacing of this story. It keeps the argument from becoming simple. If phosphine had appeared in totally clean data, with no serious chemical rival, the whole discussion would look very different. But sulfur dioxide gives the debate an immediate second path. It says maybe the weirdness is not biological at all. Maybe the problem is that Venus has a sulfur chemistry system we still do not understand well enough. And that is not a boring backup explanation. That is a major scientific problem in its own right. Because think about what that means. If sulfur dioxide is behind some of the confusion, then Venus is not calming the story down. It is telling you the chemistry itself is still incomplete. It is telling you the cloud-forming cycle, the vertical transport, the destruction rates, and the interaction between sunlight and sulfur compounds are still not under tight control. So even the non-life explanation is disruptive. In fact, one of the strongest points in the whole Venus story is that the planet may not be whispering life at all. It may be saying something just as serious in a different language. It may be saying your chemistry models are not finished. And then the story gets even bigger, because sulfur dioxide also points downward, not just upwards. ESA has explicitly noted that dramatic swings in upper atmosphere sulfur dioxide could be connected to the upward transport of volcanic gases from a large eruptio. That is not proof that this is what happened, but it is a very important possibility. Because now a gas measured high in the atmosphere may be telling you something about the planet all the way down at the surface. That connects the cloud mystery to the geology. It means the strange chemistry above the clouds might not be isolated at all. It might be the visible result of a deeper engine still operating below. And that is a major shift in how you have to think about Venus. The old version of the planet was emotionally simple. Surface catastrophe below, thick clouds above. Nothing much left to discuss except how extreme it is. But sulfur dioxide does not fit that clean picture. It suggests a planet where the atmosphere may still be coupled to active processes beneath it. Fresh gases may be rising, circulation may be moving them upward, sunlight may be breaking them down, cloud chemistry may be turning them into other compounds, and all of that may be varying over time. That is not a chemically resting world. That is a system still in motion. This is also why sulfur is really the main antagonist in the Venus story. It is sulfur that makes the clouds corrosive. It is sulfur that feeds the acid droplets. It is sulfur that complicates remote observations. It is sulfur that keeps interfering with the neatest reading of trace gas detections. And it is sulfur that may connect atmospheric variability to deeper geological activity. If Venus keeps resisting simple interpretation, sulfur is a big reason why. The same sulfur cycle that makes the planet feel toxic is also the reason scientists cannot stop looking at it. And sulfur does not just affect the phosphine debate. It also connects to other long-running puzzles on Venus, including the strange ultraviolet behavior of the clouds and the broader question of why the atmosphere looks chemically out of balance in places where people expected something more stable. Once sulfur dioxide starts varying in ways that matter, the possibility space gets much larger. Maybe the explanation is unusual, but still completely non-biological chemistry. Maybe it is linked to volcanism. Maybe it is linked to transport between cloud layers. Maybe it is a combination of all of those at once. The point is that the atmosphere stops looking closed and starts looking active. That is what makes sulfur dioxide such a powerful part of the story. It keeps showing up as the molecule that ruins easy conclusions. If you want to push toward life, sulfur dioxide pushes back with chemistry. If you want to dismiss the weirdness as noise, sulfur dioxide pushes back with long-term variability. If you want to isolate the clouds from the rest of the planet, sulfur dioxide pushes back with the possibility of volcanic input from below. At every stage, it keeps widening the case, so sulfur dioxide is not a side character in the Venus mystery. It is one of the reasons the mystery stays alive. It tells you this planet is not chemically quiet, not chemically settled, and probably not chemically understood, as well as people once assumed. And once a planet stops looking chemically at rest, the range of explanations gets wider very fast. Strange non-biological chemistry becomes more plausible. Geological coupling becomes more plausible. And even biological speculation becomes harder to completely shut down. And then the story gets even stranger, because after phosphine and sulfur dioxide had already made Venus difficult enough, another molecule entered the conversation and made the cloud chemistry look even more dangerous to ignore. Ammonia is where the Venus story stops looking like one controversial result and starts looking like a bigger chemical problem. This part needs to be handled carefully, because it is exactly the kind of claim people hear once, and then immediately turn into proof of life. And that is not what happened. In 2024, researchers reported a tentative detection of ammonia in Venus clouds at a scientific meeting, and they also discussed a possible day-night pattern in phosphine observations. Tentative is the key word here. This was not a settled peer-reviewed consensus. It was not the scientific community announcing that ammonia had been locked in beyond doubt. But even at that early stage, the claim mattered, because ammonia is not the kind of molecule you expect to hear about casually in the clouds of Venus. And the reason it matters is not complicated. Venus cloud droplets are extremely acidic. That is one of the biggest problems for any life idea there. The clouds are not just dry and strange. They are chemically aggressive, in a way that seems immediately destructive to life as we know it. So when ammonia enters the story, it changes the argument very fast, because ammonia can act like a neutralizing agent. In simple terms, if ammonia were being produced somehow inside the cloud system, it could reduce the acidity in tiny local pockets. Not across the whole planet, not enough to turn Venus into a mild environment, but enough to raise a new and very uncomfortable possibility. The clouds might not be chemically uniform. There might be tiny microenvironments where the worst part of the chemistry is being altered. That is a huge escalation, even before you ask where the ammonia would come from. Because now the question is no longer only, are the clouds too acidic for life, full stop? The question becomes, are there small regions where that acidity is being modified in ways our simple picture did not account for? That is a much more dangerous question. If the answer is yes, then the cloud deck becomes harder to dismiss with one sentence. It means the environment may contain localized conditions that are less lethal than the bulk average makes them sound. That still does not make Venus friendly. It just means the chemistry may be more internally structured than the old version of the story allowed. And that is why ammonia matters so much, even as a preliminary claim. It changes the tone of the whole cloud life discussion. Before that, the easy argument against life was that the droplets are so acidic that the conversation basically ends there. But if some process is making ammonia, then the droplets are no longer just passive acid containers. Now they become sites of active chemical modification. That does not prove biology. It does not even prove the ammonia is really there, but it shifts the conversation from the clouds are simply fatal to the clouds may contain local chemistry that is not as straightforward as we thought. That is a big change. At the same time, this is exactly where Venus has punished people before, so the caution has to stay strong. The ammonia signal was tentative, and even if future work confirms it, biology would still be only one possible explanation. Venus keeps teaching the same lesson over and over. An unexpected molecule is not the same thing as a living system. A surprising detection is not the same thing as a biosphere. The real point is smaller and more serious than that. If ammonia is present, then Venus contains another reduced or chemically surprising species in the same broader cloud environment that already gave researchers problems with phosphine and sulfur chemistry. That is enough to widen the mystery without cheating. That double uncertainty is what makes this part of the story so strong. First, the signal itself is not settled. Second, even if the signal is real, the source is not settled either. So you have uncertainty on top of uncertainty, but not the useless kind. This is the productive kind, because each layer of uncertainty forces the same conclusion. Venus is not behaving like a chemically simple atmosphere. Something about the cloud system keeps resisting reduction into one easy model. And the more that happens, the harder it becomes to treat each odd result as an isolated mistake. That is really the bigger point here. One strange molecule can always be written off as a possible artifact, a possible misidentification, or a possible dead end. Phosphine alone can be dismissed as one disputed line in one difficult observational problem. Ammonia alone can be filed away as a preliminary claim that still needs stronger confirmation. But when multiple atmospheric oddities keep clustering around the same broader cloud system, the story changes. Then the case becomes less about any single miracle molecule and more about an environment that keeps refusing to simplify. That is a much stronger and more unsettling conclusion, because now you are no longer asking only whether one gas is real. You are asking whether Venus's clouds are running a set of chemical processes that our baseline picture has underestimated. Are there reduced species appearing where we did not expect them? Are the droplets chemically evolving in place? Are there strong day-night differences, vertical differences, or localized regions where the rules change? The frightening part is not that one clean biosignature has been found. The frightening part is that the chemistry may be broad, active, and difficult enough that even the non-biological explanation could force a major rewrite. And that is why ammonia is so useful in this story, even without overselling it. It acts like another fracture in the old confidence that Venus is chemically boring above the clouds. It tells you that researchers are no longer just arguing over one controversial claim from 2020. They are now forced to think about a bigger pattern, a cloud system that may contain multiple unexpected ingredients, multiple unresolved observations, and multiple ways for the chemistry to become more complicated than the old model allowed. That is a stronger kind of suspense than one dramatic headline, because it suggests the problem is systemic, not isolated. It also raises the stakes for future missions in a very direct way. If ammonia or some other reduced nitrogen chemistry is eventually confirmed in the Venus clouds, the consequences would spread far beyond one planet. It would force researchers to ask how such chemistry is being sustained, whether the droplets are being buffered locally, whether the atmosphere contains previously missed pathways, and whether some environments that look instantly fatal in bulk measurements might contain smaller niches with very different conditions. Even if biology turns out not to be involved, that would still be a major result for planetary chemistry and for how scientists think about atmospheric habitability more broadly. So the right way to hold this section is with caution and pressure at the same time. No, ammonia is not established. No, it does not prove life. No, Venus has not suddenly become a confirmed biological world. But the fact that ammonia can even enter the conversation in a serious way tells you how far the planet has moved from the old, closed-case picture. Venus is back in play, not because scientists have a clean answer, but because the cloud chemistry keeps generating new reasons not to look away. And then the next problem gets worse, because even before phosphine and ammonia pushed Venus back into the spotlight, the planet already had an older atmospheric mystery that scientists had never fully solved. Long before phosphine pulled Venus back into the headlines, the planet already had a major atmospheric mystery that scientists could not fully explain. Its clouds absorb ultraviolet light much more strongly than expected, and for decades researchers have argued over what exactly is doing that absorbing. That matters because it means Venus did not suddenly become suspicious in 2020. The planet was already giving scientists a chemical problem they had not solved. The dark patterns in the clouds were there the whole time, and they kept pointing to the same uncomfortable fact. Something important in the atmosphere was missing from the model. That is a big reason this story has so much weight. Venus was already hard to explain before the life debate got louder. Scientists had been looking at those cloud patterns for generations and seeing a signal that clearly mattered, but not being able to fully identify the absorber behind it. So when later arguments about phosphine, sulfur chemistry, and cloud habitability appeared, they landed on top of an older mystery, not into an empty field. That makes the whole case more serious. Venus was already chemically strange. The newer debates just made that harder to ignore. And this is not just about how the planet looks. The missing ultraviolet absorber is not a cosmetic problem. It affects how Venus handles sunlight in the atmosphere, which means it affects heating, radiative balance, and the movement of the atmosphere itself. Once you understand that, the stakes become much clearer. This is not a detail that only matters for color images or surface appearance. It matters because it changes how energy is processed in the cloud layers. If you do not know what is absorbing a meaningful part of the incoming ultraviolet radiation, then your picture of how the atmosphere works is incomplete at a very basic level. That has direct consequences for everything else. If the clouds are absorbing ultraviolet light through chemistry you do not fully understand, then your models of temperature structure, circulation, and even cloud behavior become less secure. And Venus is already hard enough to model because its atmosphere is so dense, so dynamic, and so chemically layered. So the UV absorber mystery is one more sign that the cloud system is not just passive weather. It is an active chemical environment, and parts of that environment are still not pinned down the way scientists would like. That is why this older mystery fits so well into the broader Venus story. It tells you the atmosphere has been resisting simplification for a long time. Before anyone was arguing over whether some strange gas might be biological, scientists were already dealing with the fact that the clouds seemed to contain a strong absorber they could not fully explain. That is a much more solid foundation for suspense than one controversial detection. It means the planet has a history of giving off signs that the chemistry is richer, messier, and more structured than the standard simple picture suggested. More recently, that mystery got a stronger chemical lead. A 2024 study pointed to iron-sulfur chemistry inside Venusian cloud droplets as a plausible source of the long-debated ultraviolet absorption. The important part here is not to present this like a final answer that closes the case. The important part is that it gives scientists a grounded candidate that makes the clouds look even more chemically active than before. Instead of treating the absorber as some vague unknown, researchers now have reason to think mineral phases formed through iron-sulfur reactions inside the droplets could be doing a lot of the work. That is exactly the kind of update that makes Venus more interesting without making it simpler. The clouds may not just be sulfuric acid droplets sitting there under sunlight. They may also be hosting heterogeneous chemistry involving sulfur, iron, minerals, and changing particle properties inside the droplets themselves. That is a stronger and more realistic kind of complexity than the earlier versions of the mystery sometimes suggested. It says the cloud deck may be a place where trace metals, sulfur compounds, and aerosol chemistry interact in ways that can actually shape the planet's energy balance. And that matters because it raises the level of the whole conversation. Once the clouds start looking like a place where particles, dissolved species, sunlight and circulation are all interacting in chemically meaningful ways, the atmosphere stops looking like a simple blanket and starts looking like an active system with its own internal structure. That does not mean life is involved. It means the environment itself is more elaborate than people assumed. And in the Venus story, that is often the more important point. The chemistry keeps getting deeper, even when the answer stays non-biological. That is also where discipline matters, because this is the kind of mystery that can easily be exaggerated. The ultraviolet absorber is not evidence for life. It should not be presented that way. Some astrobiologists have considered whether microbes could be related to the dark cloud features, but the more likely explanations have focused on particles, crystals, and chemical compounds, including iron-related and sulfur-related possibilities. That is the honest position. The point is not that the dark cloud streaks are secretly organisms. The point is that Venus has enough unresolved aerosol chemistry to keep biological speculation from disappearing completely, even while the stronger explanations remain chemical. That actually makes the story better, not weaker. If the UV mystery were clearly biological, the case would be simpler. If it were completely solved and chemically trivial, the case would be less interesting. But Venus sits in the harder middle ground again. The clouds show a real physical effect. The absorber matters for the atmosphere. Plausible non-biological candidates exist. And yet the overall cloud chemistry still keeps expanding as scientists look more closely. That is a very Venus kind of result. The planet keeps refusing both easy proof and easy closure. And once you combine that with everything else, phosphine claims, sulfur dioxide variability, tentative ammonia discussion, and now the long-running UV absorber problem, the pattern becomes hard to miss. The cloud deck is not just some generic background layer above a dead world. It is a chemically structured environment with unresolved inputs, unresolved transformations, and unresolved links between particles, gases, sunlight, and circulation. Even if there is no life there at all, the clouds may still function like a suspended chemical system that is much more organized than the phrase dead atmosphere makes people expect. That is the subtle but important point this section has to land on. Venus clouds may not be biologically inhabited, but they may still be chemically inhabited in the sense that they contain ongoing processes, local interactions, and structured behavior that scientists are still trying to untangle. Minerals may form in droplets. Sulfur species may shift with altitude and light. Ultraviolet absorption may depend on particle chemistry that changes over time and location. That is not empty weather. That is an active environment. And once an atmosphere starts looking that active, astrobiology pays attention whether life is there or not, because that is the real threshold. The moment a cloud system becomes complex enough that energy, chemistry, particles and circulation are all feeding back on each other in unresolved ways, the line between dead weather and a truly active environment starts to blur. And Venus keeps pushing into that zone, not by giving clean biological proof, but by refusing to behave like a chemically simple world. And then the next problem becomes even harder, because even if the clouds have the right temperature and pressure in one narrow layer, and even if the chemistry is more active than expected, there is still one brutal limit that may crush the easy version of the life story completely. The hardest problem for the life idea on Venus is not the heat, and it is not even the acid by itself. It is the lack of usable water. This is the point where the easy version of the story starts to break. In 2021, a major study looked at the water activity inside Venus's sulfuric acid cloud droplets and came to a very serious conclusion. The value was calculated to be at or below 0.004. For active life on Earth, the known lower limit is about 0.585. That is not a close call. That is not a narrow miss. That is a gap of roughly 2 orders of magnitude. So when people talk about life in the Venus clouds, this is the number that hits hardest, because it says the problem may not just be that the environment is extremely. It may be that there is simply not enough biologically available water for known life to function at all. That is why this result changed the tone of the debate so much. Before that, a lot of the discussion could stay inside a more familiar idea. People could say maybe extremophiles are tougher than we think. Maybe acid-loving microbes can survive more than expected. Maybe life can adapt in ways that surprise us. But water activity is a deeper limit than that. It is not just a question of whether water molecules exist somewhere in the droplets. It is a question of whether living systems can actually access enough water to carry out the basic chemistry of life. That is a much harsher test, and Venus appears to fail it very badly by every known terrestrial standard. That distinction matters because people often hear that a place has trace water and assume that might be enough for hardy microbes. But trace water is not the same as usable water. Water activity measures how available that water really is to biological systems. A place can contain water in a chemical sense and still be so hostile that cells cannot actually use it to stay active, grow or reproduce. That is what makes the Venus result so severe. The cloud droplets may contain water in some amount, but the environment appears to lock that water away so strongly that known life cannot operate with it. So the problem is not just dryness in the ordinary sense. It is that the droplets may sit beyond a deeper physical limit that biology on Earth has never crossed. And that gets even worse when you put the acidity back into the picture, because Venus is not forcing the life idea to survive one extreme at a time. It is forcing it to survive several at once. The cloud particles are thought to contain sulfuric acid at roughly 80 to 98% by mass. That is already a brutal chemical environment. Then on top of that, the water activity looks catastrophically low. So the cloud life idea is being squeezed from both directions at once. The droplets are highly acidic, and the amount of biologically available water inside them may be far below what known cells need even to remain active, let alone build a stable ecosystem. That is what makes Venus such a severe astrobiology target. From far away, that 50 to 60 kilometer altitude band sounds like a loophole. The pressure is better, the temperature is better, and the surface horrors are far below. But once you look at the droplets themselves, the loophole starts closing. The narrow physical window may still be chemically uninhabitable in practice. That is the key point. You can solve the temperature problem enough to reopen the discussion, and you can solve the pressure problem enough to take the atmosphere seriously, but the water problem may still kill the whole biological idea before it begins. And this is not a minor objection that believers can just wave away. This is the strongest anti-life argument in the entire Venus story. If you want to be honest about the science, this is the section where the optimism gets hit as hard as it possibly can. Because now you are not just saying Venus is difficult. You are saying Venus may violate a limit that appears fundamental for active life as we know it. That is a much bigger claim than saying the environment is unpleasant. Plenty of Earth organisms survive unpleasant environments, but no known terrestrial life remains active below that water activity floor. That is why this result became such a serious reality check. At the same time, this does not kill the mystery. It actually sharpens it. Because now the question becomes much more demanding. If some atmospheric anomaly on Venus survives scrutiny, if some chemical pattern keeps resisting ordinary explanation, then the implications get harsher, not softer. Either life there would have to be doing something beyond anything known on Earth, handling water stress and acid stress in ways no terrestrial organism can match, or Venus is running a non-biological chemical system that we do not yet understand. Those are both major outcomes. So the water problem does not make the story smaller. It raises the standard so high that any remaining anomaly becomes even more important. That is where the Venus debate stops being a simple maybe microbe story and becomes a much bigger test. Are Earth's biological limits universal? Or are they just the limits of one biosphere on one planet? Most scientists will very reasonably lean toward the conservative answer until evidence forces them otherwise. But Venus keeps creating the uncomfortable setup for that question. The planet gives you one narrow atmospheric zone that looks less impossible, then cloud chemistry that looks more active than expected, then weird trace gas debates. Then this water activity result comes in and slams the door almost shut. Almost, but not cleanly enough to end the argument. That is why the story keeps its grip. Because every time Venus looks promising, physics pushes back hard. The temperature looks less hopeless at altitude, but the droplets are still ferociously acidic. The cloud deck looks chemically active, but the available water may be far below what known cells can use. A strange gas appears, then the data get attacked. A new chemical possibility enters the discussion, then the environmental limits make it look even harder. The whole subject keeps moving like that. Progress in one direction gets hit by a deeper problem from another direction. And that is what makes Venus feel so difficult, in a way Mars does not. Mars mostly challenges you with scarcity and history. Venus challenges you with contradiction. It invites astrobiology in with one hand and pushes it back out with the other. It gives you a region where life is physically discussable, then makes the droplets look chemically devastating. It gives you atmospheric oddities, then reminds you that the bulk environment may sit outside the limits of all known active life. That constant reversal is what gives the story its pressure. So the honest conclusion here is not that the life idea is dead, and it is not that the life idea is secretly winning. The honest conclusion is that Venus is forcing the question of habitability into a much more uncomfortable form. Maybe the standard Earth-based limits really are universal, and Venus is simply a brilliant example of a planet that can imitate biological intrigue without ever crossing into biology. Or maybe those limits are not the full story, and a world like Venus is where that failure becomes visible first. Right now, science does not have the evidence to choose confidently between those options. That is why this section should leave you feeling cornered rather than satisfied. The water activity result is powerful enough to crush the easy version of the life story. It tells you that even in the most interesting part of the atmosphere, the droplets may still be beyond what known biology can use. But Venus has built this whole mystery by refusing to stay easy. Every time the case looks closed, some unresolved chemistry pulls it open again. Every time the argument opens, some hard physical limit pushes it back. And once you get trapped between those two facts, the next question becomes even more extreme. If anything could exist there at all, it would not just be surviving the environment. It might have to be changing the environment around itself to stay alive. The most radical version of the Venus life idea is not that ordinary microbes could just float into the clouds and somehow be fine. It is that if life exists there, it may have to keep changing the environment around itself just to stay alive. That is a much more extreme claim. It means life would not merely tolerate the Venus clouds, it would have to actively resist them. It might need to produce compounds that reduce acidity in tiny local pockets, change sulfur chemistry around the droplets it lives in, or build protective layers that slow down chemical damage. In other words, the organism would not just be an extremophile in the normal sense. It would be something closer to an environmental engineer, constantly modifying its immediate surroundings so the bulk atmosphere does not destroy it. That is the point where this story becomes much harder to keep inside familiar biology. On Earth, a lot of extremophiles survive by tolerating conditions that are harsh, but still within some range life can handle. Venus may be asking for something more than tolerance. It may be asking for active control at the microscopic level. If the droplets are too acidic and the water activity is too low in the average environment, then any hypothetical life form might need to create tiny zones where those limits are partly shifted. Not across the whole cloud deck, not enough to change Venus at planetary scale, but enough to make survival possible inside a droplet or on the surface of a particle. That is a much more demanding picture of life than people usually have in mind, and this is where the idea gets tested very hard. In 2022, a major study looked at proposed sulfur-based metabolisms that had been suggested as ways life might explain some of Venus's atmospheric oddities. The result was blunt. The candidate metabolisms that were examined could not reproduce the atmosphere in a self-consistent way while matching the observed chemical conditions. That matters a lot, because it means some of the more popular speculative pathways were not just waiting for more evidence. They were actually checked against the chemistry, and they did not work well enough. If life exists on Venus, it is not going to be explained by one easy borrowed model from Earth. That is a very useful reality check, because it removes the comfortable version of the hypothesis. It tells you that this is not just a matter of finding an acid-loving sulfur microbe on Earth and imagining the same thing drifting into Venus. The atmosphere on Venus is too chemically strict for that kind of shortcut. Proposed metabolisms have to fit the observed gases, the reaction pathways, the cloud conditions, and the energetic limits all at once. When researchers tried that with some of the better-known sulfur-based ideas, the fit was not good enough. So the easy biological story gets weaker right there. But this is also exactly where the mystery becomes more serious instead of collapsing. The failure of those proposed metabolisms does not prove there is no life. What it proves is that the simple biological options are weak. That is an important difference. If the atmosphere still contains real disequilibrium, still shows unresolved chemistry, still produces debates over molecules and cloud processes, then one of two things has to give. Either the chemistry is more exotic than people expected, or any possible biology would have to be more exotic than people expected, or both. That is a much bigger and more unsettling version of the problem than just saying maybe familiar microbes are hiding in the clouds. And that is the real escalation in this section. The question stops being, could Earth-style life maybe survive there if it were very tough? The question becomes, if this is life at all, would it have to use strategies we do not see on Earth, or only see in much weaker form? Would it have to manipulate acidity in ways no known organism can sustain under those conditions? Would it need protective coatings that change the behaviour of the droplets around it? Would it have to use chemistry that is so unlike standard terrestrial metabolism that current models barely know how to test it? The harder the environment becomes, the more strange the biology would have to be, and that raises the stakes instead of lowering them. This is also where the older Venus astrobiology arguments become useful again. Long before the phosphine controversy, researchers had already pointed out that the Venus atmosphere contains many of the elemental ingredients life cares about: carbon, hydrogen, oxygen, nitrogen, sulfur. That older line of thinking was never saying present-day Venus looked easy for life. It was saying the cloud layer deserved attention because the raw ingredients were there, and because the altitude structure created a narrow region worth studying. Modern work has not really destroyed that older intuition. What modern work has done is make the constraints much harsher. The ingredients may still be there, but the actual biochemistry now looks much more punishing than the early cloud life idea once seemed. That is an important correction because it keeps the story honest. The old cloud life concept was not foolish. It identified a real atmospheric window and a real scientific question. But since then, better studies have shown just how severe the acid conditions are, how low the water activity may be, and how hard it is for proposed biological pathways to match the observed atmosphere. So the modern version of the Venus life debate is not a repeat of the old optimism. It is the same basic idea under much tougher rules. The door is not wide open. The door is barely open at all, and anything passing through it would have to be far stranger than the first versions of the hypothesis assumed. That is why Venus has become such a hard test, not just of planetary science, but of biological imagination. Maybe the wrong question is, could Earth life survive on Venus? That question may be too narrow to be useful now. The harder question is whether life, given enough time and enough pressure from a collapsing planetary environment, could invent survival strategies that have no close match in terrestrial biology. Not magic, not anything outside chemistry and physics, but still something far outside our standard examples. That is the uncomfortable possibility Venus keeps forcing into view. At the same time, there is no license here to jump from possibility to conclusion. There is still no confirmed life, no confirmed metabolism, no confirmed mechanism by which a Venusian organism could neutralize droplets and remain active in such a hostile cloud system. The stronger point is more careful than that. If anything biological exists there, it would likely have to be doing environmental control at a level that current easy models do not capture. And if nothing biological exists there, then the unresolved chemistry still demands an explanation. Either way, Venus is pushing scientists into a zone where the usual assumptions are starting to look too limited. That is what makes this section so important. It takes the life idea out of the comfort zone entirely. No simple extremophile analogy works cleanly. No off-the-shelf sulfur metabolism works cleanly. No easy version of cloud habitability survives the strongest constraints. So if the mystery persists, the next step is not easier biology. It is stranger biology, stranger chemistry, or both. And that means Venus is no longer just a test of whether life exists there. It is a test of how narrow our definition of viable life has really been. And then the story gets even broader, because the chemistry in the clouds may not only be coming from the clouds, the whole planet underneath may still be active right now, feeding the atmosphere from below and making every signal even harder to interpret. The Venus mystery gets even harder when you realize the clouds may not be acting alone, because the planet below them may still be active right now. Up to this point, the story could still be treated as mostly atmospheric. Strange gases, strange droplets, strange chemistry, all happening high above the surface. But that picture starts to change once geology enters the case. If Venus is still volcanically active, then the atmosphere is not just a place where odd chemicals appear for unknown reasons. It may be getting fresh material from below, and that changes everything, because now the cloud chemistry is no longer a separate puzzle. It may be connected to the interior of the planet itself. That is one of the biggest stake raisers in the whole Venus story. A geologically active planet can keep feeding gases into the atmosphere, keep changing the chemical balance, and keep creating signals that look unusual from orbit or from telescopes. That means some of the things people want to explain with exotic atmospheric chemistry, or even with life, might instead be tied to a world that is still moving heat and matter upward from below the surface. The moment you connect volcanism to cloud chemistry, the whole mystery becomes more coherent, but also more dangerous, because now you are not dealing with one strange layer in isolation. You are dealing with a whole planet that may still be chemically restless from core to cloud tops. And there is a strong reason scientists take that seriously. In 2024, researchers reanalyzing old Magellan radar data reported evidence of new lava flows at additional sites on Venus that built on earlier work that had already pointed to signs of recent volcanic change. NASA's Jet Propulsion Laboratory described this as the second direct geological evidence of recent volcanic activity on Venus. That is an extremely important result. It means the old idea of Venus as a planet that did all its major geological work in the distant past, and then mostly froze into a static state, is getting harder to defend. The surface may still be changing. The planet may still be erupting on geologically recent timescales, and maybe even on timescales that matter right now. That matters far beyond geology, because once lava flows and volcanic activity enter the conversation, the atmosphere becomes much easier to disturb without needing biology at all. A volcanically active Venus could inject sulfur-bearing gases, heat, and chemical inputs into the atmosphere in ways that reshape what researchers detect above the clouds. So if you are trying to explain sulfur dioxide swings, strange cloud chemistry, or trace gas anomalies, active volcanism becomes one of the first things you have to account for. Not because it solves every mystery, but because it gives the planet a direct way to keep changing its own atmosphere from below. That is where the link back to sulfur dioxide becomes especially important. Sulfur dioxide has already been one of the key troublemakers in this story. It helps build the sulfuric acid clouds. It varies in ways scientists are still trying to explain. And it keeps interfering with simple interpretations of other signals. If volcanic plumes or deep atmospheric transport are still feeding sulfur-bearing gases upward, then some of that variability may not be coming from cloud chemistry alone. It may be the visible result of an active interior, and once that possibility is real, the story changes from mysterious gases appear in the sky to the sky may be chemically connected to a planet that is still erupting underneath. That is a much bigger and much more serious situation, because then the atmosphere is not just a place where molecules drift around and react under sunlight. It becomes the upper end of a planet-wide engine. Material may be moving from the interior to the surface into the lower atmosphere, and from there upward into the cloud deck. Circulation can then spread those gases, sunlight can break them down, droplets can process them, and cloud chemistry can turn them into even more complicated signal. That is a far more dynamic picture of Venus than the old closed-case version ever allowed. It also shows how little of Venus we have really resolved. Magellan transformed Venus science in the early 1990s, but the fact that researchers are still mining that dataset for major geological discoveries decades later tells you how unfinished this planet still is. We are still extracting first-order facts about recent volcanic activity from old radar data because Venus has not been revisited with the same level of sustained, detailed attention that Mars has received. That gap matters a lot. For Mars, scientists have built a much richer picture over time, with repeated missions and many overlapping measurements. For Venus, huge parts of the modern story are still being pulled out of limited or old observations. So when people talk about Venus as if it is already well understood, that confidence is not really justified. We know enough to say the planet is extreme. We know enough to say the surface is brutal. We know enough to say the atmosphere is thick, hot, acidic, sumic, and chemically complex. But we do not yet know the current level of geological activity with the kind of global and time-variable monitoring that would count as normal for a planet this important. We do not have the same repeated, high-resolution, modern coverage that would let scientists track changes the way they want to. That means even now, Venus is still capable of surprising researchers with discoveries that would feel more basic than they should at this stage. And that unfinished state is exactly why geology makes the whole life debate harder. If Venus were clearly geologically dead, then atmospheric oddities would have fewer obvious sources. The case for unusual atmospheric chemistry would become more isolated. But if Venus is still geologically alive, then every trace gas becomes harder to interpret. A gas might be created by photochemistry, or by transport between cloud layers, or by volcanic input, or by some combination of all three. That does not make life impossible, but it raises the burden of proof again. Because now biology is competing not just with abstract chemistry, but with a planet that may still be actively injecting chemical surprises into its own sky. And this is why a volcanically active Venus is not just more interesting, it is more unsettling. It means the planet is not a static ruin. It is still moving matter, still recycling chemistry, still changing the atmosphere from below. The old picture of Venus as a dead warning label becomes harder to hold once you realize the world may still be actively reshaping itself. And that makes the atmosphere more deceptive. A living geology can create some of the same kinds of unresolved signals people are tempted to read as signs of something biological. Not because the planet is alive in the biological sense, but because an active interior can keep the chemistry out of equilibrium and keep the case open. That is what raises the fear factor in this part of the story. Maybe life is not the answer. Maybe the answer is that Venus is still geologically active enough to mimic some of the complexity people usually associate with living systems. But that does not calm things down. It makes the planet more difficult. Because now even a non-biological answer is telling you Venus is far more dynamic than the old story allowed. And if future data eventually show that both active geology and unresolved cloud chemistry are real at the same time, then the case becomes even more disruptive. Because once you accept that Venus may still be feeding its atmosphere from below, the next question gets bigger. If the planet is active now, then what was it like in the past? And did it ever have a surface environment where life could have begun before everything changed? The past of Venus may be even more important than the clouds above it now, because the whole life question changes depending on which history is true. There are basically two very different versions of ancient Venus, and they lead to two very different conclusions. In one version, Venus may once have had liquid water on the surface, more temperate conditions, and enough stability for habitability to exist for a meaningful stretch of time. In the other version, Venus was dry very early, never truly became an ocean world, and moved towards extreme conditions so fast that the usual story for life starting there becomes much harder to defend. That split matters a lot. If Venus once had a milder surface, then life could have begun there long ago and later been pushed upward as the planet became more hostile. But if Venus never really had that kind of world, then even the cloud life idea has to start from a much stranger place. That is why the ancient Venus question sits underneath everything else in this story. It is not just background history, it changes what kind of explanation you are even allowed to take seriously. If Venus once had oceans or long-lived surface water, then the planet becomes easier to imagine as a lost, habitable world, one that may have started with conditions more familiar to us and then collapsed into the extreme greenhouse state we see today. In that version, the cloud hypothesis has a path, Life could have had a normal origin early, then survived through a planetary disaster by retreating into the atmosphere. But if Venus was effectively dry from very early on, then that path starts to disappear. Then you are no longer talking about a familiar biosphere adapting to catastrophe. You are talking about life beginning under conditions that may have been alien from the start. One of the biggest reasons scientists long suspected Venus once had much more water comes from the deuterium to hydrogen ratio in its atmosphere. This is one of the classic clues in the case. Venus has a much higher ratio than Earth, commonly described as more than 100 times Earth's value, and often cited in the rough range of 120 to 150 times terrestrial, depending on altitude and data sets. The meaning of that is important. Hydrogen escapes to space more easily than deuterium because it is lighter. So when you see a very high deuterium to hydrogen ratio, it suggests that over long periods of time, a planet has lost a lot of the lighter hydrogen and been left enriched in the heavier form. In simple terms, it looks like the fingerprint of major water loss. That is why the deuterium clue has been so influential for so long. It gave scientists a reason to think Venus may once have had a much larger water inventory than it has now. Not necessarily an exact Earth twin, not necessarily blue oceans covering the whole planet for billions of years, but at least a world that may have started wetter and then lost that water over time. Once that interpretation became part of the story, Venus started to look like a planetary tragedy. A world that may have had some chance at habitability, then crossed into runaway greenhouse conditions, lost water to space, and ended as the extreme planet we see today. That is one of the most emotionally powerful versions of Venus, because it turns the planet into a failed Earth-like world. But then the newer challenge comes in, and it hits that story hard. More recent work, including a 2024 to 2025 study, argued that Venus' interior may actually be very dry. The study suggested volcanic gases on Venus would contain at most around 6% water mole fraction, consistent with a planet that may have finished its magma ocean phase already desiccated and then stayed dry for most or even all of its later history. That is a serious blow to the easier ancient ocean picture. Because if the interior really is that dry, then Venus may never have had the kind of long-lived surface oceans many people had in mind when they imagined a younger, more habitable Venus. That is a major change in tone. It means one of the simplest origin stories for Venusian life starts to weaken. The old version says maybe Venus once had water, maybe life began under conditions closer to early Earth, and maybe what we see now is the remains of a world that lost almost everything. The dry interior result says not so fast. Maybe Venus did not lose a long, stable ocean world. Maybe it was dry or near dry very early, and maybe the window for Earth-like surface habitability was much smaller than people hoped. Or maybe it never really existed in the way the popular story imagined. If that result holds up, then the most comfortable version of the cloud life hypothesis is in serious trouble. And that matters because the old ocean story made the life idea easier to motivate. If you say Venus once had surface water and milder conditions, then life starting there does not sound so strange. It sounds like a reasonable extension of what we already know from rocky planets and early planetary evolution. But if Venus never had those long-lived surface oceans, then you lose that bridge. Now the question becomes much harder. Any life in the atmosphere would either have to come from a much more limited and less Earth-like early environment, or it would have to originate under conditions far stranger than the old models assumed. That is not impossible by logic alone, but it pushes the hypothesis into much more extreme territory. At the same time, this part of the story should not sound finished, because Venus is still one of the least well-constrained major planets in the solar system when it comes to detailed long-term history. Its past is being reconstructed from incomplete evidence, sparse direct sampling, atmospheric ratios, geochemical reasoning, and a limited set of remote observations. So the dry interior result is powerful, but it is not the kind of result that magically ends the argument forever. What it really does is raise the stakes for future missions and future modelling. It turns a long-running intuition into a sharper, testable claim. Was Venus once a wetter world that later died, or was it close to a near runaway state from the beginning? That question matters well beyond Venus itself. It affects how scientists think about the inner edge of the habitable zone around stars. If Venus once had surface water, and only later crossed into a runaway greenhouse. That tells us one thing about how close a rocky planet can get to its star and still remain habitable for a significant time. But if Venus was dry very early and never truly entered a long-lived ocean phase, that tells us something else. Then the threshold for stable habitability may sit farther out or behave differently than many models assumed. So when scientists argue over ancient Venus, they are not just arguing about one planet. They are also arguing about how to interpret rocky exoplanets around other stars. And this is where the emotional weight of the whole video really comes together. Because beneath all the arguments about phosphine, sulfur dioxide, ammonia, acid droplets and volcanic gases, there is a more basic fear. What exactly was Venus before it became this? If it once looked more like Earth, then Venus becomes a lost biosphere story. It becomes the story of a habitable world that may have had the ingredients, and maybe even the opportunity for life, and then suffered a planetary transformation so severe that any surviving biology would have had to retreat into the sky or disappear completely. That is a disturbing idea because it means habitability can be lost on a planetary scale without the planet becoming scientifically dead. But if Venus never had that Earth-like phase, the implication is not comforting either. In some ways it is even stranger, because then any life associated with Venus would have to be rooted in conditions much more extreme than the usual origin story allows. Then Venus is not the graveyard of a once habitable world. It is evidence that the starting conditions for life might be broader, harsher, and less intuitive than we think. That would force a much deeper change in how scientists think about where life can begin at all. So either way, ancient Venus becomes the emotional core of the whole mystery. If it once had oceans, then this is a story about a world that lost them, and maybe took an early biosphere down with them, or trapped some remnant in the cloud. If it never had oceans, then this becomes a story about whether life, if it exists there, began under conditions that would already have looked deeply alien to us. One version makes Venus tragic, the other makes Venus even more unsettling. And the reason this matters so much is that both possibilities lead to a rewrite. Venus is either the remains of a habitable world that went catastrophically wrong, or it is proof that our assumptions about how and where life can begin have been too narrow from the start. There is no small outcome hiding in that split. Either path changes how we think about habitability, climate history, and rocky planets near the inner edge of a star's habitable zone. And then there is one more pressure acting on this whole story from above. Because Venus is not only shaped by its atmosphere and its interior, it is also still losing parts of itself to space right now. Venus is not just being changed from below and from within, it is also being stripped from above, and that makes the whole planet harder to understand. One of the biggest differences between Earth and Venus is that Venus does not have a strong intrinsic, global magnetic field like Earth's. That matters because Earth's magnetic field helps shield the upper atmosphere from direct interaction with the solar wind. Venus does not get that kind of protection. Its upper atmosphere is much more exposed, which means habitability on Venus has never been only a surface question or a cloud question. It is also a space weather question. For billions of years, the sun has been hitting this planet directly, helping strip material away, reshaping the upper atmosphere, and slowly changing what Venus can keep and what it loses. That is a major part of why Venus matters so much. Long-term atmospheric loss changes everything. It affects whether a planet keeps water, whether it keeps the right balance of gases, whether oxygen-bearing compounds build up or vanish, and whether the atmosphere remains stable enough for habitability to last. So when people ask how Venus became so dry and so hostile, one part of the answer is not only greenhouse heating and volcanic history, it is also that the planet has been losing pieces of itself to space for immense stretches of time. The sun has not just been shining on Venus, it has been wearing it down. One of the strongest examples of that came from work based on Venus Express data, which showed that Venus has an electric wind strong enough to accelerate ions and help remove the components of water from the upper atmosphere. That is a very serious fact. The electric field involved was described as roughly 5 to 10 times stronger than Earth's in that context. So even if Venus once had much more water, the planet had a built-in way to help tear that inventory apart over long timescales. Water molecules can be broken apart, the lighter and charged pieces can be accelerated, and over time that contributes to the long-term loss of habitability. That matters because it gives Venus another mechanism for becoming the planet it is now. It is not just that the surface became hot and the atmosphere became dense. It is that the upper atmosphere also became a zone where the ingredients of water could be pulled away. That makes the ancient Venus story even harsher. If the planet started wetter, then it did not just dry out at the surface. It also had a way to keep leaking that water inventory to space. The damage was happening from more than one direction at once. And the story gets even sharper when you add more recent observations. In 2024, results from Bepi Colombo reported cold oxygen and carbon ions escaping from Venus in a part of its induced magnetosphere that had been much less explored. The measured ion fluxes were on the order of 2 × 10 to the 3 per square centimetre per second, and the carbon ions were found at about 10% of the oxygen ion abundance in the detected outflow. The exact numbers matter less than the basic conclusion. Venus is not only a planet that lost atmosphere in the distant past. It is a planet that is still leaking material into space now. That is a very important shift in how to think about Venus. Sometimes people hear about atmospheric loss and picture something ancient, dramatic, and basically finished. But Venus is still interacting with the solar wind in ways that matter. It is still losing ions. It is still part of an active exchange between the planet and surrounding space. So the atmosphere is not just a leftover from a long-closed chapter. It is still being shaped in the present. That makes every chemical reading harder to interpret, because what you see in the atmosphere is not just the result of local cloud chemistry or geological input from below. It is also being sculpted from above. That is why atmospheric escape matters so much to the life story, and it matters in 2 different ways. First, it helps explain why Venus ended up dry and chemically harsh. If the planet once had more water, escape processes help explain how that inventory was reduced over time. Second, ongoing escape means the atmosphere is not chemically quiet. Gases are being altered, particles are being removed, and the upper atmosphere is being constantly shaped by processes that can erase, distort, or imitate the kinds of signals scientists might otherwise want to interpret in biological terms. A planet that is being actively eroded from above is not giving you a clean laboratory signal, and that is exactly why Venus remains so difficult. The lower atmosphere may be getting fed by volcanism, the clouds may be running complex sulfur and aerosol chemistry, the upper atmosphere may be losing material to space, so the whole planet is being worked from both directions at once. Matter can come up from below, get processed in the middle, and be stripped from above. That is one of the worst possible setups if you want a simple answer. It means any trace gas can potentially reflect several different processes at the same time. It may be produced deep below, transformed in the cloud deck, and affected again in the upper atmosphere. This is where simple interpretations start to fail completely. A strange gas is not automatically a biosignature if the planet is under continuous atmospheric erosion. A chemical imbalance is not automatically evidence of life if the atmosphere is being fed from below and stripped from above at the same time. And a harsh environment is not automatically dead if the same planet keeps producing enough motion, transport, and disequilibrium to generate unresolved patterns. Venus keeps putting scientists in that exact trap. Every time you try to isolate one process, the planet reminds you that several are happening at once. That is why atmospheric escape is not just a side note in the Venus story. It is part of the full siege. Greenhouse heating below help destroy surface habitability. Acid clouds in the middle create one of the most chemically aggressive environments in the solar system. And solar stripping above keeps pulling at the upper atmosphere even now. Venus is being attacked from every direction at once. And still inside that assaulted system, scientists are finding enough unresolved chemistry to keep talking about the possibility of life. That is what makes the whole idea so unnerving. Because if anything is alive there, it is not living on an easy planet with one problem to solve. It would be surviving inside a world that has spent eons trying to erase the conditions life normally depends on. The surface is hostile. The droplets are hostile. The water availability is catastrophic. The chemistry is unstable. The geology may still be active. And the upper atmosphere is still leaking to space. Venus is not just hard. Venus is under constant pressure at every level, And yet the mystery still does not go away. That is what gives this section its weight. Venus is not only a climate disaster and not only a chemistry puzzle, it is a planet under long-term assault. And the fact that researchers still have enough unresolved data to even discuss habitability inside that system makes the whole story much more intense. Any life there would not be thriving in peace. It would be surviving in the middle of a planetary environment that has been stripping away habitability for billions of years. And after all of that, the next step becomes very concrete, because this story cannot stay trapped in old data and arguments forever. The real test is now going to come from the missions that are finally being built to go back and measure Venus directly. After all the arguments, all the reanalyses, all the contested signals, this story is finally moving into the phase that actually matters: direct measurement. Venus is not just waiting for more debate now, it is waiting for missions, and that is what changes the tone completely. For years, this topic lived in a frustrating space where the chemistry looked strange enough to keep the mystery alive, but the data were messy enough to stop anyone from closing the case. That phase is ending. The next decade is when Venus starts getting interrogated properly. NASA's DAVINCI and VERITAS, along with ESA's EnVision, are aimed right at the questions that made this whole story so difficult. What is really in the atmosphere? How active is the surface? And how tightly connected are the clouds, the crust, the interior, and the gases moving between them? That is why this part is so important. The Venus story is leaving the rumour phase and entering the measurement phase. Up to now, too much of the case has depended on remote spectra, hard to untangle signals, old radar data, and models fighting each other. Those things matter, but they leave too much room for ambiguity. The next leap will come from going back to Venus with instruments designed for exactly these problems. That means the biggest future change in this whole story probably will not come from one dramatic paper or one headline molecule. It will come from missions that can move through the atmosphere, map the planet at much higher quality, and connect surface activity to atmospheric chemistry in a much more direct way. DAVINCI is probably the clearest example of that shift, because it is built around the atmosphere itself. This mission goes right at the part of the Venus story that keeps causing the most arguments. NASA has described it as a mission to study Venus's origin, evolution, and present state in unprecedented detail, and one of the biggest goals is to help determine whether Venus was ever wet and habitable in the past. That matters because DAVINCI is not staying at the level of uncertain telescope signals. Its descent probe is meant to go through the atmosphere and sample it directly. That means noble gases, trace species, pressure, temperature, wind, and the chemistry of the layers people have been arguing about for years. And that is exactly why DAVINCI matters so much to the life debate. If the atmosphere contains strange trace gases, this is the kind of mission that can help sort out what is really there and what is not. If the cloud layers contain chemical gradients that matter, this is the kind of mission that can move through those layers instead of inferring everything from far away. NASA's mission material describes measurements from about 67 kilometers altitude down to near the surface. That means DAVINCI is going straight through the environment that sits at the center of this entire controversy. Not around it, not past it, not one step removed from it, through it. That is a completely different level of evidence from arguing over distant spectral lines. And once you understand that, you can see why DAVINCI is so dangerous to weak ideas on every side. If phosphine is there in some meaningful way, a mission like this can help reveal where and how much. If the atmosphere is running strange sulfur chemistry instead, a mission like this can help expose that directly. If the ancient history of Venus is written into noble gases and isotopic clues, DAVINCI is built to go after those too. So this is not just another Venus mission. This is one of the best chances scientists have had in a very long time to confront the atmosphere with tools designed for the job. Then there is VERITAS, which goes after the other half of the mystery, the hidden planet below the clouds. Because one of the biggest problems in the Venus story is that people keep trying to explain the atmosphere without fully knowing how active the surface still is. If volcanism is feeding gases upward, that changes everything. If the crust is deforming, resurfacing, or still linked to an active interior, that changes everything too. NASA says VERITAS will map Venus's surface to determine its geologic history and test whether volcanism and related processes are still active. That is exactly the question Venus needs answered if researchers want to stop guessing about how much of the cloud chemistry may be coming from below. High-resolution topography, radar imaging, and deformation mapping are powerful tools in this context because they can turn broad suspicion into measurable planetary process. Right now, a lot of the volcanism discussion depends on limited evidence, old Magellan data, and signs that are exciting but still incomplete. VERITAS can change that by giving scientists a much sharper view of the surface, the tectonic structure, and the kinds of changes that would reveal whether Venus is still geologically active in a way that matters right now. If sulfur dioxide variability in the atmosphere is being partly driven by volcanic input, this is the kind of mission that can make that link much harder to ignore or much easier to reject. That is what makes VERITAS so important for the life story, even though it is not looking for life directly. If Venus is still erupting, then a big part of the atmospheric weirdness may come from geology, not biology. That would not make Venus less important. It would still mean the planet is far more active than the old closed case version suggested. But it would give the chemistry a harder, more grounded explanation. And if VERITAS finds that the surface is quieter than expected, then some atmospheric puzzles get more interesting, because one major non-biological source becomes weaker. Either way, the mission raises the quality of the whole debate. Then EnVision broadens the case even more, because by now it should be obvious that Venus is not a one-layer mystery. ESA has described EnVision as the first mission designed to provide a complete view of Venus, from inner core to upper atmosphere. That is the right way to approach this planet now, because the story no longer fits inside separate boxes. Atmospheric chemistry, cloud physics, volcanism, interior activity, surface history, and atmospheric escape may all be linked. If that is true, then you do not just need one mission looking at one piece. You need a system-level mission that tries to connect the layers. That is what makes EnVision such a strong addition. Its fact sheet highlights very high-resolution radar imaging and the first Venus subsurface radar sounding instrument. That means it is not just looking at the visible surface structure. It is also trying to understand what lies below, which matters if Venus is still geologically active, in ways that shape the atmosphere from beneath the crust upwards. Once you combine that kind of subsurface probing with global imaging and atmospheric context, you start building the kind of full planet picture that Venus has been missing for decades. And that is really the point of this whole section. The future of the Venus mystery is not going to be decided by arguments on social media, and it is not going to be settled by people repeating the same headlines from years ago. It is going to be decided by going back, by descending through the clouds, by measuring the chemistry directly, by mapping the crust in detail, by looking for signs of active volcanism, by probing below the surface, by tying the interior, the atmosphere, and the cloud deck into one connected system instead of treating them like separate stories. That is why this topic feels so charged right now. For the first time in a very long time, Venus is lined up not just for speculation, but for interrogation. And once those missions start delivering, the next section of this story gets brutally simple. If the data come back clean, then either Venus really is hiding something extraordinary, or it is about to teach us how a dead-looking world can imitate life better than we ever expected. The most important thing to understand is that this does not need to end with cities, signals, or anything dramatic in the science fiction sense. It does not need intelligent life. It does not need large organisms. It does not need anything you could see with your eyes. A single confirmed microbial biosphere in the clouds of Venus would already be enough to force a major rewrite of planetary science. That alone would mean life can persist inside sulfuric acid droplets, above a surface destroyed by runaway greenhouse conditions, on a planet most people would have called uninhabitable without hesitation. And that would change the subject immediately. The question would no longer be whether life needs Earth-like comforts. The question would be how far life can go before our definitions stop working. That is the version of this story that matters most, because it is much more serious than the movie version. The scariest possibility is not aliens in the usual sense. It is biology refusing to stay inside the environmental limits we thought were reasonable. If something is alive in the Venus clouds, then life is tougher, stranger, and less dependent on stable surface conditions than a lot of our thinking has assumed. That would force scientists to rethink the lower limits of habitability, what counts as a credible biosignature, and how many places in the universe may be more biologically plausible than they currently seem. And that would hit exoplanet science especially hard. Venus already matters there because it sits near the inner edge of what people think of as the habitable zone. It is one of the main reference points for the question of how close a rocky planet can be to its star before it becomes too hot and unstable for long-term habitability. If Venus never had oceans, that changes one set of assumptions. If it once had oceans and lost them, that changes another. But if Venus has life in its clouds right now, then a third and much stranger possibility opens up. Some planets that look too hostile at the surface may still have atmospheric niches that matter. That would be a huge shift. It would affect how scientists interpret spectra from rocky exoplanets, which gases they focus on, and how seriously they take atmospheric disequilibrium under extreme conditions. Right now, a lot of thinking about habitability still starts with surface environments, liquid water in familiar settings, and something broadly Earth-like in climate and chemistry. Venus would complicate that immediately. It would say surface habitability is not the whole story. A planet can fail one test and still remain chemically or biologically interesting in another layer. And if that is true, then some of the planets we currently classify as too hostile may need a second look. That is one reason Venus is such a dangerous object scientifically. It keeps pushing against simple categories: not habitable, habitable, dead, alive, Earth-like, non-Earth-like. Venus keeps sitting in the middle and making those labels look too clean. And if life is really there, then the implications spread far beyond one world. Suddenly, cloud decks, upper atmospheres, and chemically extreme environments on other planets become much more important. Scientists would need to ask not just whether a planet has the right surface, but whether it has a stable, atmospheric refuge where life can persist even after the surface becomes hostile. And that would make Venus even more disturbing in relation to Earth. Venus has always been part of climate discussions because it is so close to Earth in size and yet so different in outcome. It is the nearby example of a greenhouse world taken to the extreme. But if life exists there, that warning becomes more complicated, not less. It would mean climate catastrophe and loss of surface habitability are not necessarily the end of biology everywhere on a planet. A world can become almost unrecognizable at the surface and still possibly preserve some biological holdout somewhere else. That is not comforting. It means planetary collapse may not erase life cleanly. It may trap life in smaller, harsher, more desperate refuges. That is what makes Venus more than a simple cautionary tale. The easy version says Venus is what happens when a planet goes too far and becomes dead. But a living Venus, even at the microbial level, would say something darker. It would say a planet can become a ruin and still not be fully sterile. It would say life can survive not because the world stayed stable, but because it retreated into the last place available. That turns Venus from a warning about climate into a warning about endurance. The planet may not only show how habitability is lost, it may show how biology hangs on after the loss. But the final twist is that the non-life outcome is almost as important. Suppose the future missions come back and show that phosphine was misread, ammonia does not hold up, and every major anomaly ends up tracing back to sulfur chemistry, active volcanism, cloud microphysics, and atmospheric transport. That would still be a revolutionary result. It would mean Venus fooled us, not because it was alive, but because planetary atmospheres can generate levels of complexity that imitate some of the signals people attempted to read as signs of life. That lesson would be incredibly valuable, especially for exoplanets, where the data will often be weaker and much harder to interpret than anything we can get from Venus. That point really matters, because exoplanet astronomy is going to depend heavily on indirect evidence. Scientists will be reading faint atmospheric spectra from worlds they cannot visit directly for a very long time. If Venus teaches us that a geologically active, chemically disequilibrated, cloud-filled planet can mimic some biosignature-like behavior without any biology involved, that becomes a critical warning. It tells us not to overread strange gases. It tells us not to confuse atmospheric complexity with life too quickly. It tells us that dead worlds can be far more chemically creative than we wanted to believe. So either way, Venus forces a correction. If life is there, then biology is tougher than expected. If life is not there, then planetary chemistry is more deceptive than expected. Both outcomes break something important in our current assumptions. Both outcomes force scientists to rethink how they classify worlds, how they interpret atmospheres, and how careful they need to be when moving from strange chemistry to biological claims. And that is really the line this whole story has been building toward. The terrifying idea is not just that there could be life on Venus. The terrifying idea is that either Venus hosts a form of survival we did not think biology could achieve, or it hosts a level of planetary chemistry we did not think non-living worlds could sustain. Either answer is disruptive. Either answer forces a rewrite. Either answer changes how we think about habitability, biosignatures, exoplanets, and the limits of life itself. That is why Venus has become one of the most dangerous planets in science again. Not because we have certainty, not because anyone proved the case, but because the uncertainty stopped being small. It became rich enough, technical enough, and consequential enough that ignoring it now would be less scientific than facing it. Venus is dangerous because it sits right on the line where two major assumptions may fail at once. Maybe life can go farther than we thought. Maybe dead planets can do more than we thought. Venus may be about to show us which one is true, and if the next missions finally break this case open, the result will not just tell us something about one planet next door. It will tell us how wrong we were about what counts as alive, what counts as dead, and how thin the line between those two categories really is. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video